Good morning, mathematicians. What's poppin' today? Hopefully everyone had a productive week full of theorem reading and theorem proving.
Mathematicians.
Reading your favorite textbook and such. You can see I have a whole bunch of tabs open today. Been looking at a lot of stuff for research. So I think I mentioned the other day some bittersweet news about the research. We've through discussing with my collaborators, we discovered, there's some more interesting stuff that we could say to put in the paper. And, I'm just hungry to get the paper out there. But, if you can say more interesting stuff, then you should. So, this is actually from the first part of the paper. The paper I'm currently working on is like a sequel to this one I've got open here. I wasn't an author on this first one though, but I was looking for some relevant information to what we're trying to do. So, let's see. Let's pop open one note here. I know I started really late again today. Probably some of you thought it wasn't happening. Okay, I thought I had some fun facts for you today, but now, of course, I can't remember what it was I was going to talk about. If people have questions, that's always the best way to get things going. Oh, you know what I'm going to start with, actually? There was something on Reddit, and I'm gonna say something controversial here that a lot of mathematicians would disagree with, I guess. Something I shouldn't say, probably. I don't know. Where did I put it? Okay, yeah, so there's this post. It's math and addiction. Pretty addicted to weed last year. Gave me a cure for boredom. Took a lot of mental capacity. Quit weed this year. Decided to focus on university. Getting addicted to staying up late doing problems. Very much can relate. Actually, when I was in high school, I was drawing. I was failing pre-calculus because I was skipping class to go smoke weed, but then I was teaching myself calculus also simultaneously with a book from the library, and I was like drawing it on marker on my bedroom walls late at night while I was high, and my mom thought I was losing my mind. Big puzzle, feel like you're unlocking secrets of the universe. Few days ago, smoked first joint, felt fantastic. And then, just talking about how the universe is beautiful and thinking about math. I don't know. First off, I don't know. I think this guy's post is great. It's just a post about loving math and weed too, I guess. But I also don't recommend it because I'm probably stupider because of the weed that I smoked when I was younger. So don't do drugs, kids. They're bad for you. But or don't do a lot of it, or try them when your brain's fully developed or something. But your brain's fully developed, so you're not gonna make good decisions like waiting until your brain's fully developed. So, yeah. Anyways, I made this comment here, and I said if I wasn't so obsessed with making these strange scribbles on paper, probably make more meaningful contributions to society and be at least upper middle class. Yeah, I'd be less poor instead of a poor ass grad student eking out a couple papers that like 10 people read. Maybe more than 10 people, actually. I don't know. Some of these papers, well, this paper coming up could be cool. Every few months, I try again, teach myself something useful. And then all of a sudden, I'm looking at categorical local language, right? And this person makes this comment. I'm just gonna. Where am I jumping to here? Yeah. Okay. They said something. They said something about all math. Will be applied someday. Like, oh, you're part of the engine that makes society work. And then the math you're interested in will be useful for society at one point. It's people like you that laid the groundwork for this to happen. I don't know. So I have a comment about this. I'll basically just tell you my thoughts. I'll put it on screen. I'll tell you my thoughts. But the thing is, like, so it's definitely true that eventually very pure math can get applied, right? So whatever Hardy we used to be going on about how beautiful number theory is, and it's beautiful because it will never be applied, which is I also think that's an annoying attitude. Like, as a pure mathematician, I used to be like this when I was younger too, but to be like, oh, so holier than thou about your little pure math that's completely useless, like, it seems like a stupid thing to be all mighty about. Anyways, he ended up being wrong, right? Because of like things like elliptic curve cryptography and RSA and stuff. There's all sorts of interesting number theory now that's very real world and practical. Simply, well, not just him, but I don't know if anyone had imagined that it would really be all that useful back in the day. So, obviously these things change, right? But at the same time, I think it's also not true that all math will eventually be used, right? There are many, many mathematicians in history, right? Like the Gausses and Eulers and Newtons and everything. Those weren't the only people doing math at that time, right? There's a lot of other mathematicians that we've forgot about. There's a lot of people's works that we've forgotten about, a lot of papers that have just sort of like disappeared, and ideas that have just disappeared because, they get published and then it just never really mattered. And there's probably things that have been rediscovered by people that we don't even know. I mean, there's definitely cases of things being rediscovered and then only after that, like someone will publish a paper and then only years later they discover, oh, someone else had like published it first, but it was some tiny hidden little publication somewhere. So I really do want to push back on this idea that all math is applied eventually, because like and also it's definitely, there's a spectrum, right? Like, clearly, if I'm doing like biostatistics, that is more readily applicable to the real world than some crazy like abstract whatever nonsense that like the stuff I work on or something, right? And so I think I think this myth gets repeated both by mathematicians and people who aren't even mathematicians. So I feel like they understand even less about what math is about and what it does and what mathematicians do. So it's even funnier that people ardently defend this position that, oh yeah, all math is useful and important and blah blah blah. I mean, I should sort of be defending that idea, especially at a time when, like in the States, like funding is being threatened to all sorts of things, and like I don't want to see less funding across the mathematics, and Yeah, and it is true, like that the pure math discoveries, are important too, and are intertwined with analysis or applied math. But at the same time, it's just like it's not given. It is not a guarantee that any of my work will ever be applied. Like there's this paper from my undergrad on graph theory. Maybe a few people read it back in the day. I don't know. Actually, it might have some citations. But I highly doubt. For like funding purposes, we wrote. For funding purposes, we wrote cited by 8. Okay, so that's, I don't know. That's pretty good. That's pretty cool. But lost my train of thought here. But the thing is, like, yeah, I just don't like after those citations, like I don't think this paper will ever actually be used in applications. Well, this is actually more likely to be used in applications, to be honest, than what I'm currently doing. So this is more believable. But like it was one little paper, and then it happened, and then and it is true that like all of these, I mean, at the same time, it is true that all of these small discoveries are still little drops that contribute to the entire pond, right? So even though there might be many, many mathematicians whose names and work are now forgotten, I mean, they still made little contributions, and, they pushed some examples a little bit further, and then maybe, those papers were still useful for the more famous mathematicians to see that, and then to go, oh, okay, like, some work, there's some other work there, and then I can see, like, this bigger structure and whatever, and people go on. But and that's fine. So I guess you can say that everything has a non-zero contribution, but it's also a matter of like where on the gradient it is, right? So like, I mean, borrowing a page from this, like there's this idea of effective altruism, right? And so the basic idea is like, okay, say you want to be altruistic, you want to improve the world in some way, but what's the most effective way to do that, right? Is like just donating to random charities and doing nothing else? Is that the most effective way to positively influence the world around you? I don't know. It's well, it's good to ask these questions. Or even, let's just say you want to donate to a charity, right? Let's just say you want to donate to a charity. Certainly some charities are better than others, right? There are charities out there that have been caught up in scandals, or people embezzling money, or sometimes they're just not very effective. Like they end up spending too much money on, they might even mean well, but they're just not very good at effectively spending money. So you want to look into that a bit, right? And you want to try and make a decision about, what's the most effective way that I can positively impact the world around me. Well, if you want, I mean, if that's something that you want to do, right? If that's something you want to do, you should think logically about the most effective way to do that. Hi, Jens. And so I think bringing this back to mathematics, I mean, we talk about, all math is applied eventually, like all math is important. But there's clearly some math that is more directly applicable to the real world, that helps people and affects the real world one way or the other much more immediately than other math. And you can say, oh yeah, but you never know when the next big thing will come from. But yeah, that's kind of the point. It's like, yeah, we can play the lottery of digging deep in the well of pure mathematics, waiting for the next very useful thing to appear, or we can use the tools that we already have to make the world a better place. I mean, we can do both, right? We can also do both. There's no reason that we have to completely halt one to do the other, right? But it's also about what proportion of eggs do we put in that in either basket. In the same way that, like, I I do think space exploration is cool. I do think it's an admirable goal. I do think we should build bigger particle accelerators to smash atoms open, and I think we should go to Mars, and I'm all for all of that stuff. However, people like to give this argument that somehow it's a huge altruistic thing to work towards those, and that it's for the benefit of humanity in general. And I just don't buy those arguments because there's like there's so much shittiness happening in the world today, and we have the tools already to fix a lot of shittiness. Like, we could just fix the shittiness. We don't need bigger tools to fix a lot of the shittiness in the world. And so I just think it's a question of like where to allocate our resources, our time, and our energy. So in the same way, when it comes to mathematics here, again, like I say in this post, I do math because I like to do math. In fact, I like to do math because I think I'm addicted to it. I would say I'm addicted to doing mathematics. I'm like, oh, like I say in this post, I'm like, oh, I should learn some statistics, so maybe I can get like a decent job afterwards. But then I just end up finding myself doing abstract mathematics like a couple hours later. Like, it's just how it goes. It's not even within my control. It's not much different than someone that has like a gambling problem or something, honestly. And so for me, like, I'm making the decision to do mathematics, or sometimes not even making the decision, out of enjoyment, right? I don't view this as some sort of like altruistic. I'm contributing to the foundations of human knowledge or whatever. I think that a lot of people like to tell themselves that story because it sounds very selfish, right? To just pursue something just because you want to, right? And people want to believe that their work has some meaning, has some greater impact. They want to feel like their work is important in contributing to society. But I feel like sometimes you just can't have it both ways, I just don't think that a lot of very crazy pure math really offers that much, at least in proportion to, say, well, applied math, or just a lot of other stuff that one could be doing in the world. Like, being a doctor is probably the most impactful thing I think one could do, or I don't know, a construction worker even, or a janitor or something like. So now maybe you don't. Now again, maybe you want to like optimize how many lives you impact, right? So like, okay, someone who picks up garbage, the garbage man. Very important job, very essential job, but okay, you're like, the actual sphere of influence is maybe not a ton. Like, I guess, well, depending on the city you're in, the areas you patrol is like thousands, hundreds of thousands of people you directly impact. But, maybe you want to aim bigger. You want to try and really influence people through time beyond your generation. Well, then, I don't know, biomedicine or something. I just don't. I just feel like it's so much more of a gamble. It could happen. It could happen that with pure math, you make some sort of fundamental discovery, RSA encryption, right? Or and then you could even argue that there's some facts about like fundamental number theory that probably are actually due to Euler or Gauss or something that you use in RSA encryption, and it's like that goes on to impact humanity, maybe not forever, but for a long time, well after those names are gone. But that is such a gamble. That is such a gamble. Even if you want to stick to mathematics, there's just so much more you can do that immediately impacts the world with like applied math or statistics. So I mean, I've been ranting about this now for like 20 minutes, but yeah, I just want to try and dispel this myth because I think it gives people an easy out. Hey, XML. I think it gives people an easy out to hide and to make excuses. And so again, for me, that's not a problem because I don't feel, I mean, maybe call me an immoral person, but I'm not like, oh, I need to go out and do the most I can for all of humanity. I don't feel like my job needs to be some deep, meaningful thing that contributes to all of society. But some people do, right? And I think a lot of people, instead of really thinking carefully and taking a long, hard look at themselves about what they're doing and asking if what they're doing is the most effective way to impact the world, that they're lying to themselves by just saying, oh, all math is applied eventually. It's the easy answer so that you don't have to look inside at those hard questions and really evaluate if what you're doing matters or is meaningful. But yeah, I mean, XML, I am always looking for things to talk about. My preferred thing to do on the stream is if people have questions, especially if they're questions I know how to answer. I have just kind of been yapping for like 20 minutes about the sociology of mathematics, but Jens is also right that it is a very fun topic. I think it's an important topic, and I think my stance is one that's not popular. Like most mathematicians take the opposite stance because again they wanna feel like their work matters. And again, really, I should say pure mathematicians because I feel like applied mathematicians are much more. Of course, these lines are murky, right? There's applied mathematicians who just write very theoretical papers all day, nonetheless. But yeah, I don't know. Well, you've been reading a bit about Hopf algebras. Can I say anything about that? Nope. Not really. I probably should be able to say something more about that because it does show up in the background of my work. In fact, there's some like growth and deep group of representations that I work with that are that turns out to be a Hopf algebra. You put a Hopf algebra structure on that. Also, like the I could be misremembering, but the whole fact that like I could be misremembering. So take this with a grain of salt. Fact check me here. But I mean the category of K algebras. Well, the opposite category is equivalent to, say, the... oh, hey, Nicole. I think you were in some live streams. I think you popped up in some live streams a while ago, but I don't know if I've seen you recently. But yeah, so K algebras, the opposite category of K algebras is equivalent to the category of schemes, or affine schemes, I should say, affine K schemes. Affine K schemes. So I think there's something here about if we look at like an algebraic group over a field, and you go back over to this category, I think maybe that you get a Hopf algebra or something out of it. Again, I barely remember this stuff. Oh, right. You asked about thesis, right? It's great that you asked about that question, because I think that was my most popular live stream. Probably because thesis writing was in the title. I'm sure a lot of people searched that. So I had a whopping like 700 something views. My most viewed live stream to date. Could I give some idea of where K theory comes from? As in the actual subject? Yes, I can. And then there's also a question here about any idea how to show that for A in GLNR, determinant greater than 0, A squared equals X for some in real matrices? Possibly. I'll at least yap about it to help help get you started on that. But let's talk about K theory first, where it comes from. So, again, I am, despite my channel name, I'm not an expert in this topic. So, do your own research. Funny how one little sentence changes so much, changes meaning over time and has so much more context. But yeah, look into things more on your own. But so is my understanding there's algebraic K theory and there's topological K theory, and really they're not so different, but actually they kind of are. And I think that topological K theory existed first. And well, the thing is, so I guess I've never really studied higher K groups. For me, I've always studied, there's what's called the Grothendieck group. Of an abelian category. So you basically just take what are elements of this group. Well, you just take isomorphism classes of objects, and if there exists a short exact sequence, ABC, then you say that B is equal to A plus C. Yeah, which K theory are you talking about? Yeah, okay, oh, so they are very different. Yeah. I mean, yeah, so I think topological K theory evolved out of the theory of vector bundles. Well, okay, I'll try and say something that I think is maybe not nonsense about the relations between these things. Because, yeah, there may be... well... I think like topological K theory and algebraic K theory ultimately diverge a lot eventually, yes. But as I've said on the stream before, like there's so many things in algebraic geometry which, to me, if you look at that thing in algebraic geometry and you ask why is it defined like that, it is just so not clear. It's so not intuitive to me. But if you go and you look at the corresponding concept in differential geometry, you're like, oh, yeah, that makes sense. And then normally, like this happens time and time again, there's like, here's this definition in differential geometry that makes total sense. It's equivalent to this other thing, but then in the algebraic world, this original definition doesn't make sense because you don't have such a nice topology, but this alternative definition is worked in such a way that it still can be translated over to the algebraic world. And so my understanding is that's kind of the roots of how algebraic K theory grew out of topological K theory. But yeah, okay, maybe nowadays they're very different. So yeah, topological K theory. So the very basic, the like K0 group. This is like, you know, asking about the group pi 0 when you've got all the higher fundamental groups. And actually that's more than just an analogy. But so the Grothendieck group, so let's see an example. I mean, the standard, let's look at the category of finite dimensional K vector spaces, right? The most vanilla abelian category that could exist. What is the growth and group of this? Well, there's one element for each isomorphism class. Well, I should say I've been a little bit sloppy. So we take it's formal sums of isomorphism classes. So really what you should do, I mean, if I wanted to be rigorous, and also, by the way, this is where I first got into an existential crisis about large cardinal axioms, because, for example, the category of finite dimensional vector spaces is it's a large category. Like if you wanted to stay in just traditional ZFC, well, you can't, because the even the amount of one-dimensional vector spaces is too big to be a set. So what you have to do is you sort of take like the free group generated on the objects, and then you quotient out by these relations. But then in order to take a free group, you need to know that this is a set. So technically you need to take a large cardinal axiom. I mean, you can also wave your hands and say, oh, well, it's a class, and then I can just collapse to isomorphism classes. Yeah, it is essentially small. I agree. But then, but then there's still like issues about like choosing a skeleton and stuff, and like the way that I do stuff in my work, it's just easier to work with the actual sheaves. I mean, here's the thing is, the point is, it's fine now, and I think you should believe in large cardinal axioms. I believe in large cardinal axioms now, and I think you should too. That's the real takeaway. So, anyways, so we take this growth and degroup. What is it for the category vector spaces? Well, we need one object for the for each isomorphism class. Well, finite dimensional vector spaces are entirely determined by their dimension. So we basically just have well, let me write it. So we have the class of just the zero vector space. We have the class of k to the 1. We have the class of k to the 2, etc. But then we also have like formal sums of these. So and we also need the negatives, right? So well, yeah, basically just from this equation, right? If we have like the k into k2 into k, this is like the direct sum or something, right? So actually, even here, right? Even here, like again, using the fact that it's essentially small is like not a good idea, because like clearly these two vector spaces are like isomorphic, but then strictly set theoretically, like they're different. So those are already two different representatives, and you don't want to have to juggle with representatives. So yeah. Anyway, so this tells you that like, yeah, the class of K2 has to be the class of K1 plus the class of K1, etc. So anyways, the takeaway from this is that this just ends up being the integers, right? You just have these formal, it's isomorphic to the group of integers. Now, so this is basically K0. There's let's see here, Chris and Ginsburg. I've used this book so much. It is definitely one of the foundational texts for my thesis. Let's see their equivariant K theory. Yeah, so they say something about the K ring in general here. One of their perspectives on the K ring. Where is it here? I thought they defined it near the beginning. They defined it. I thought as like you take like the fundamental group of like a nerve of the category. Ah, yeah. Here we go. Right. So, So here was Quillen's approach to higher K groups for abelian categories. I mean, here we're talking about equivariant coherent sheaves, whatever. But yeah, Quillen associated to any abelian category a simplicial complex B plus C. So I'm guessing that this is the nerve of the category. So okay, for those who know, but yeah, somehow you associate a simplicial complex to your category, and then you define the higher K groups to be the homotopy groups of that simplicial complex. So this actually applies to any abelian category. And then so K naught just recovers the ordinary Grothendieck group, but then of course we have like these higher K groups and things get like crazy fast. And you can sort of see that, like, okay, this is, like, if we're talking about abelian categories, like, that's very much algebraic, but you can also believe here's why K-theory has anything to do with homotopy theory as well. Well, because it literally does. Because it's literally defined as kinds of homotopy groups. But yeah, so going back, I think the original idea for K-theory was actually, so instead of just looking at vector spaces, one then studies the category of vector bundles over some sufficiently nice topological space. I think I have some... Oh, I don't know if you guys, tell me if you love this idea or hate it, but I could go through all my old course notes in a series of streams. I have like basically all the courses I've taken in a folder and all my tech files. Well, obviously there was many courses I took before I started teching, but I tried to get started early. I have some notes I made once upon a time where for some course I learned a little bit about the topological K-theory, because there's actually a way to prove, there's this little paper I found once where you can prove the fundamental theorem of algebra for polynomials over the octonions, which, okay, you have to be super careful about what you mean by that because they're not even associative. So, like, how do you define the multiplication structure? But, and you actually use, like, vector bundles in K-theory to prove it. So cool. I'll have to dig up that paper. But, yeah, so I think K-theory originally evolved out of studying, like, the Grothendieck group of the category of vector bundles. And then I think... Yeah, I'm not sure originally how the higher K groups were defined, but that's where it originally comes from. And then this also isn't the first time on stream that I've mentioned that, like, okay, that's for the analytic world. We want to study vector bundles in the algebraic world. That definition doesn't really work. So what do we do instead? We study coherent sheaves or maybe quasi-coherent sheaves. And then one can play the same sorts of games. There's also this really cool theorem. So this is, as I understand it, this has something to do with K-theory. But there's this cool theorem. It's called the Serre-Swan theorem, where it turns out that for a sufficiently nice topological space, so... what is it? It's I forget the conditions. There's some quasi-compact, quasi-locally, I don't even remember. But we have it turns out that the category of vector bundles for some nice enough real manifold is equivalent to the category of projective modules over the ring of smooth functions on that manifold. Well, this is the analytic version, and I recall, and there's also like an algebraic version, and that's also kind of, so I really don't know anything about algebraic K-theory, but from the a little bit of flipping through books that I've done, I know that you study projective modules a lot, and I think that this is one of the like fundamental ideas behind that. Okay, let me talk about this question. I don't even know if person's still in stream, but let's see if I can say something about this question. So A is in GLNR. The determinant of A is greater than 0. Is that where Lie algebras originate from? No, I don't think that's where Lie algebras originate from. I mean, I can't say for sure, but no, I don't think so. So A is in GLNR. A has determinant greater than 0, and we want to prove that there exists some x in GLNR such that A squared is exp of x. Right. So, yeah, Lie theory is definitely older. I'm also pretty sure of that too. Okay, so why would this be true? Well, that's interesting. I mean, so let's think. I believe that if you're, I could be wrong. I could be spitting crazy stuff here, but I think that if you have a Lie group, and if you took the connected component of that Lie group, then I think the exponential map is surjective. So if I think it is surjective. I could be wrong about this. What does the capital / lowercase mean in notational standard? I'm not sure what is so this uppercase here is this is the Lie group GLNR. This is the group of all n by n invertible matrices. The lowercase here, this is the Lie algebra. These are supposed to really, if I could write math frac, I would write math frac. So this is just the collection of all n by n matrices, not necessarily invertible. Okay, so is the exponential? So I think it might be surjective. And so in that case, then the determinant of A being greater than 0. This is in the component of the identity. So, yeah, GLN basically has two components. So the connected component, the identity component of GLNR should be what we might call GLN R plus. So this is just the collection of all matrices with positive determinant. And so therefore, if I'm remembering correctly, of course, this is another thing we would have to prove. Therefore, there should exist an X in GLN R, at least such that, well, I mean, if A... actually, okay, so this is even easier. I mean, if A has positive determinant, then so does A squared, right? So A squared also has to belong to here, and so since that's in the connected component, then this much is true. But okay, we would have to prove the claim. I would have to convince you of this claim. Why is that true? And that's a good question. I mean, I feel like we're getting into the territory then that we should also probably consider the matrix logarithm. Um, yeah. Yeah, so actually this is an interesting, I mean, this question, I'm not even sure where the a squared comes from. Oh, suppose x is surjective, then for any a, yes. Yeah. So I think that's exactly right. Yeah, you want to. So if you already knew that you had an x, if you already knew that you had an x, so that x was a, then you should just take x 1/2. Absolutely. That should get you. If you knew that this was true, then you would take this. That should be true to get square roots. Yeah. Yeah. So you wrote a squared is x over 2 squared. Yeah. 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 Yeah, that's about true. That should be true. Anyways, I might call it there for today. We'll see. We'll see. I mean, it's a beautiful day. I should get outside. You should get outside. Go prove some theorems on a bench in a park. Um, exp. Sorry. Oh, let's see here. Wait. Exp. A is x over 2 squared. Is that true? Wait, what are we supposing? Oh, we're starting with a. Ah, yes. Okay. Sure. Right. If we knew that a is x, then this should be true, which tells us that square roots exist. Sure. Yeah. By the way, what's your definition of exp in general? Matrix exponential or something else? Well, I don't remember the general. Actually, it's funny. This came up in a conversation I was having yesterday related to. I was giving like a mini talk for some research purposes on some background, but that came up. So in Fulton Harris, I think, yeah. I mean, when I'm writing exp here, I just mean matrix exponential. But exp, like, there's a pretty general definition from a Lie algebra to the Lie group, and if we're just working with GLN or some like sub algebra therein, then yeah, you can just take the matrix exponential. So you just copy the definition from the Taylor series of the ordinary exponential, but of course you need to prove that this converges. Well, first you even need to say what does that even mean? What does it mean to talk about convergence of matrices? And then I believe once you define this, then you can lift that up to talking about the exponential. Been reading these Adams notes on Lie groups, and he uses a knife definition in terms of one parameter subgroups. Yeah. That's interesting. He defines it in terms of one parameter subgroups? Because I thought you needed the exponential to define one parameter subgroups. Oh, Hobster is here. That's another OG homeboy from the old days. But unfortunately, they didn't have any chicken. Well, hopefully they get more chicken in the next 40 minutes. I was actually just about to log off because it's a beautiful day here, and I finished my coffee, and I feel like I need a deeper shot of caffeine and to go for a run. Um, so, yeah. Uh, how do I know? Do I know anything about Lie algebroids? Do I know anything about Lie algebroids? Never mind. There's more questions. I'll stick around for a little bit. How do I know about? I don't know. I don't know very much about Lie algebroids. There was once actually, I sat in on a seminar about Lie algebroids when I was doing my master's. But I haven't retained very much information about it at all. Sort of the background for that is I mean, we started talking about stacks and descent theory, which are topics that came up recently, and yeah, I just didn't retain much. Actually, recently I was looking back on my notes because I've been re-inspired to try and learn more about stacks. So yeah, might revisit that again soon. Maybe I should do a stack stream. I have all these ideas and not enough hours in the day to do different streams. I've thought about the idea of like doing a stream where like I just stream while I'm teaching myself about stacks. But like maybe that's like on one hand, maybe that's very boring because a lot of it will just be me sitting here and like talking out loud about trying to understand stacks. But then I don't know, maybe if I put on like lo-fi study beats or something in the background, it can just be a parasocial study sesh. I don't know. Yeah. Okay, I am gonna go now. For real. I'm gonna go jog, get some oxygen in my brain, and then I'm gonna. Yeah, I am an aspiring stack broker for sure. Yeah. Okay. Thanks everyone. Go prove some theorems.